In the second screencast for Chapter 2, we will discuss the different kinds of chemical bonds, how these bonds affect some of the physical and chemical properties of molecules. We'll also look at oxidation reduction and acids and bases. Chemical bonds are attractive forces between two atoms. There are three basic types of chemical bonds: ionic, covalent, and hydrogen. As you might surmise from the name, ionic bonds involve ions. Specifically, ionic bonds are the attractive forces between two oppositely charged ions. In table salt, sodium chloride, a positively charged sodium ion is attracted to the negatively charged chlorine ion. Ionic bonds are not extremely strong. In this example, a sodium atom gives an electron to a chlorine atom. The two ions are now bonded together with an ionic bond. A second type of chemical bond is the covalent bond. Covalent bonds result from atoms sharing one or more pairs of electrons. If the pair of electrons is shared equally, a nonpolar covalent bond results. Polar covalent bonds involve electrons that are not shared equally. You might think of these electrons as being closer to one atom or spending more time with one of the atoms. Atoms involved in polar covalent bonds do not ionize, but they do end up with partial opposite charges. I'd like for you to memorize that covalent bonds between two identical atoms are, and also the carbon-hydrogen covalent bond, are nonpolar. I'd also like for you to remember that the oxygen-hydrogen bond is a polar covalent bond. In this example, two chlorine atoms share a pair of electrons equally. A nonpolar covalent bond results. In water molecules, the oxygen atom has a stronger attraction for the shared electrons than the smaller hydrogen atoms do. The oxygen hogs the electron somewhat and ends up with a partial negative charge. The hydrogens have partial positive charges. The sigmas here represent partial charges on the atoms. Water has some surprising properties due to the polar covalent bonds and the resulting hydrogen bonds. Hydrogen bonds are our third type of chemical bond. The name is somewhat misleading. Hydrogen is often involved, but that's not a requirement. First, there must be two atoms with partial opposite charges. These are the result of polar covalent bonds with other atoms. The hydrogen bond, then, is the attractive force present between these partially opposite charged atoms. These bonds are very weak, but they're important in living things. DNA, for example, has lots of hydrogen bonds, and the shapes of proteins are influenced by hydrogen bonds. Earlier, I mentioned that water behaves strangely. These weird properties are largely the result of numerous hydrogen bonds among the water molecules and between water and other polar substances. In this illustration, the dotted lines represent some of the hydrogen bonds that are possible between water molecules. Water is a very good solvent for polar substances, but not for nonpolar things. Water molecules are adhesive and cohesive. Water has a high heat capacity and also a high heat of vaporization. Ice floats in liquid water. We'll discuss these properties further in class. Staying with the topic of water forming hydrogen bonds, substances that are attracted to water, in other words, will form hydrogen bonds with water, are called hydrophilic. They're hydrophilic because they contain some polar covalent bonds and will form hydrogen bonds with water. The opposite is hydrophobic. It's repelled by water. Hydrophobic substances are held together by mostly nonpolar covalent bonds, and as a result will not form hydrogen bonds with water. Sugar, in this example glucose, they have lots of polar oxygen-hydrogen bonds. As a result, they'll form lots of hydrogen bonds with water. They typically dissolve very easily in water. In contrast, like the fatty acid pictured here, these contain mostly non-polar covalent bonds. Water molecules form hydrogen bonds with each other, and they push the hydrophobic oil away. Jumping ahead in your textbook, I'd like to next cover oxidation and reduction. Oxidation occurs when an atom or a molecule loses one or more electrons. Reduction is the opposite. An atom or a molecule is reduced when it gains one or more electrons. These two reactions are usually linked and are often referred to as oxidation-reduction reactions. If the transfer of electrons was all that was involved, I probably wouldn't mention oxidation-reduction in this class. But something else is also being transferred with the electrons: energy. That transfer of energy is very important in the metabolism used by living organisms. Oxidation is the result of an atom or a molecule losing electrons and losing energy. For example, the release of energy from your food often involves oxidation. When an atom or molecule is reduced, it gains electrons, and in doing so, gains energy. In this reaction, NAD is the lower energy, the oxidized form of the molecule. Adding electrons and energy, in this case also adding a hydrogen atom, produces the reduced higher energy NADH. NADH is somewhat like a rechargeable battery in that it stores energy in your body. NAD is the discharged battery, which has released its stored energy and an electron. Let's switch topics now to acids and bases. An acid is a substance that releases hydrogen ions when mixed with water. Hydrochloric acid is a strong acid because it releases hydrogen ions when placed in a solution. Bases do the opposite. When mixed with water, bases remove hydrogen ions from a solution. Or in the case of bases like sodium hydroxide, they release hydroxide ions, which combine with the hydrogen ions. pH is a measure of how acidic or how basic a solution is. It's a measure of the hydrogen ion concentration of the solution. 0 is the most acidic, with lots of hydrogen ions. At the other extreme is 14, which is very basic and has very few hydrogen ions. Halfway between 0 and 14 is 7. 7 is neutral. It's neither acidic nor basic. Coming back to our definition of pH, more correctly, pH is the negative logarithm of the hydrogen ion concentration. Don't freak out on me. We're just going to use this to help explain a couple of things about pH. First, where do the numbers 0 and 14 come from? Remember exponents? Remember that 10 to the 0 power equals 1. Think of 1 as the whole thing, as many hydrogen ions as possible. I don't even know what to call 10 to the minus 14th power, but it's a really small number, almost 0. In this case, almost no hydrogen ions. One more thing, because we're working with exponents, every whole number change in pH represents a 10-fold change in the hydrogen ion concentration. That wasn't too bad, was it? It's very important that organisms be able to control the pH in their bodies. Buffers help to maintain constant pH. They do so by combining with hydrogen ions when mixed with an acid, and they do the opposite when mixed with bases. In response to the lack of hydrogen ions, they release more. Please note that adding a buffer does not mean that the pH will be neutral. Some buffers will maintain acidic pHs. Others will maintain basic pHs. Phew, that's the end of video 2.